Thank you, Julia, for the invitation. It's really a pleasure to be here. I know many people in the audience, interacted with many people over the years, and it's fun to be here and talk about these subjects, something near and dear to my heart, safe autonomy. And in the intro, I like the ratio of demos to theorems. So you can count in this. There are theorems and there are demos. So we'll see what the ratio ends up being. But that's kind of the goal, is how do we formally approach robotics? And before I begin in any talk, I really need to point out my students and postdocs. They're the instrumental element of this entire presentation. The videos wouldn't exist without them. The theorems, by and large, wouldn't exist without them. So they really make everything go. All right, so I don't think I need to say that we're in the moment of the humanoids, right? Everyone knows this. Everyone sees every other day. At first, I used to update the videos, and then I just stopped, because if I tried to grab the video of the moment of the dancing robot of the moment, I just couldn't keep up. But it's really incredible what's happened in the last, year or two in terms of humanoid robots and the way they're being deployed and the behaviors we're seeing. It's honestly mind-blowing. From someone who, back in the day, I did little simple planar walking robots, and it actually would go viral, right? And now we're in a different era. And so, of course, this extends to my lab. I have a humanoid, a G1, like many people have now. This was back in January, and I like showing this video because this was just a couple days after we got the robot in our lab. And I was doing a demo here, and there's a bunch of people standing off camera. And the robot was walking, and my student, Gary, told me during the demo that he was running our locomotion policy, in this case, an RL policy. And I was shocked that he got it working in 2 days and it was demo worthy. So this translation of getting things to actually go on hardware nowadays is incredibly fast. Of course, in my lab, we're really interested in where our heritage is, and what you'll see in this talk is model-based control methods. So we've been playing with this idea of understanding pure model-based control. So this is just MPC for humanoid locomotion, zero learning involved. And this is an RL policy, sort of the standard RL policy. None of this was sort of published, and you can see that we're trying to understand kind of how do these two things relate to one another in the lab. And that's really been what this talk is about now, is kind of the last sort of year of soul searching, let's say, together with some historic context in where control methods can actually fit in this. Because the reality is when you combine model-based with learning-based methods, you get some really special things, I have to admit. As a model-based person, as someone that loves math, you cannot deny the power of injecting math into reinforcement learning. This is an example, which I'm going to talk about later in the talk, but this is running what we call CLF RL. So it's an example of really this fusion and what we're able to achieve with it. But with the injection of learning-based methods comes this sort of distribution shift failure mode, right? That's really catastrophic. So what happens in this video is the robot, as you'll see in the next bit when it replays in slow motion, is it was walking just fine. This is just a pure RL policy in this case. And the ankles strike. So it just starts with a self-collision. That self-collision knocks the robot into a domain it wasn't trained for, right? You're out of distribution, and all of a sudden it just goes crazy. And it actually broke the ankles. It was a mess. And if you've ever played with robots, and if you look on the internet, you see all these examples of robots going crazy. It's because they're, when you train things on data and you deploy things based on that trained data, you don't really know what's going to happen, right? So the fundamental question becomes, how do we do things like guarantee safety in this context, right? What's the paradigm to guarantee safety? And how do we certify it? So that's really what this talk is about. And I'm going to make the strong statement here that I hope to defend throughout the presentation, which is that safety is the key bottleneck to the deployment of AI. That if we don't solve this safety problem, all the cool dancing videos you see online of humanoid robots will never be realized in any real-world application domain. So to add to this, let me sort of say this one more way. There's two axes that you look at with robots. There's performance and there's safety, robustness, reliability. Right now, everyone is pushing the performance axes. That's great, but it results in very brittle behaviors that, again, once you take them out of where they're trained, they can go crazy. So we need to enable those behaviors to be deployed. We need to remove the friction that safety will give, ultimately, in these ideas being deployed in the real world. And my second claim is that control theory is the way to remove this blocker. So this is also a strong statement and incredibly biased from my perspective, to be very clear, because I'm a control theorist. So of course I'm going to say control theory is going to be enable this deployment, but I can back it up with some evidence. In particular, this is an example of where control theory can play a role in what I'm going to talk about in this talk a bit, things like a safety filter. You take an RL policy, which you might be able to command to do bad things like knock over this box. You have a safety filter, which is based on control theoretic methods. In this case, it's a CBFQP. And this safety filter modulates the RL algorithm to guarantee safety without knowing what the RL algorithm is or how it operates, except that it takes a reference signal and tracks it. So we need to be able to deal with control with learning in a way that we have elements we might not be able to fully understand, that is like black box elements. And we need to have formal guarantees associated with that deployment. And this will enable things to be actually deployed in practice. So before I go into that, I want to step back for a second again on my history of where I come from. I'm a model-based control person, right? I love Lyapunov, I love barrier, I love dynamical systems, I love nonlinear dynamical systems in particular, I love hybrid system models, and this is actually now a decade-old video, so 10 years ago. And it's still pretty good. I gotta say, sometimes we forget that good things were done before like a year ago. And this is full multi-domain locomotion on a full-scale humanoid robot using just pure model-based control methods, CLFs, where we actually have springs in the ankles. So we have compliant elements at the base, and we're able to get very natural and efficient walking. This, at the time, was the most efficient locomotion ever realized on a humanoid-type robot. We've taken these ideas, and because they're model-based, we can extend them to other robots, of course. This is Cassie, which was, for a while, really the only biped robot you could buy, built by Agility Robotics, who is now deploying Digit. And we're able to apply a very similar paradigm in that case. So let me kind of talk about what that is. So let me do like a brief 5-minute primer or less, 2-minute primer on nonlinear control. Because most of nonlinear control can really be broken down to everything on the right side of this slide, in a nutshell, right? So you have a nonlinear system, just general nonlinear, typically a fine. And if you want to do something like stabilize the system, what you do is find a certificate for that stability. In this case, the certificate will be something like a Lyapunov function or a control Lyapunov function. Here I'm using Lyapunov with exponential decay. So you make sure that function satisfies a property you want, in this case positive definite, and that its derivative condition with respect to flows of the system satisfy a decay rate that guarantees the type of stability you want. And what this does by the comparison lemma says that this thing decays like this scalar dynamical system, which is clearly stable. And that implies that this V will actually exponentially stabilize. Because it's positive definite, you know that X will ultimately drive to your goal state or wherever that function V is 0, right? And so you have this theorem that if there exists a CLF, meaning if you have inputs that satisfy this derivative condition, you exponentially stabilize to the 0 level set of V. In this case, this is like a periodic orbit on your walking robot, right? So there's this nice connection that if you can find this V, you get this. Now, of course, there's great work out of MIT SOS on how you can find Vs. In the case of robotic systems, you can actually use feedback linearization to find these Lyapunov functions sort of algorithmically, formulaically. And the end result of this process is an entire class of controllers that stabilize the system, for which this is an example implemented on Cassie, clean, meaning this is CLF. Now, this works. I mean, this really does work in practice. Of course, there's a lot of caveats that I don't show in these videos. Things like state estimation took 9 months to really pin down properly. It's a big problem in realizing this stuff on robots, something that RL actually helps a lot with. So the question is, how do we take these ideas now, and how do we extend them or inform learning with the methods for model-based control that prove so effective? And so this is one example now that I showed earlier, but I want to focus on. It's a very recent result where we can take what we did with CLF QPs, and instead of generating a quadratic program controller that we put online and have to worry about things like state estimation, like I mentioned, you take these nonlinear controllers and you use it to generate the reward function for RL. In this case, our reward function is a really clean 4 terms, basically requiring that this is a CLF and that it decays as a CLF should decay. You use this in training, and then you get to use all the benefits that RL gives you, which model-based methods sort of don't. You can GPU parallelize and then domain randomize. And so you can do this massive simulation to train up the RL policy to basically emulate the model-based controller. Of course, the advantage here is we're not emulating human data. something that might only be true on one trajectory, but we're emulating this rich dynamics that's present in the real nonlinear dynamics of the system itself. And when we do this, we're actually able to deploy this in zero shot, meaning once we train this up, it actually really does work off the shelf. I'm not being sort of facetious here. We're able to lay this out. And not only are we're able to do things like put this on the robot and make it walk really cleanly, all over Caltech. It never fell once in this whole filming. It walked all over Caltech, but we're able to extend it to other behaviors because the advantage of model-based methods is they essentially have an infinite amount of data in them, if you'd like, right? If data is a bottleneck for collecting human data from video demonstration, et cetera, model-based methods have an infinite amount of data. For every initial condition, you get a trajectory, right? For every controller, you get a trajectory, right? Now you have to find them, that's the difference, but once you find them, you can do lots of really cool things. So this is a recent result we had with CLF-RL now for running. So we generate, same process. We generate from a hybrid system model, we generate a CLF. That CLF is used as the reward function in RL. We train this up and then deploy it. And we did this in about 2 weeks from start to finish. And it turns out the hardest part was actually the fact that we have visual odometry on the robot as well to get it to run straight. And that visual odometry with onboard compute and everything was kind of the trickiest part of this. Making a robot run is one thing, making it run in a straight line is another one. It's actually pretty challenging. We took it outside. It worked the first time we took it outside, meaning off the bat, and we threw a bunch of stuff at it because that's what you do with robots, right? Disturbance testing. The point is these model-based methods do fuse with RL well, in my opinion. And this is just one example of sort of the kind of things I think we can do going forward to take away some of the hackery of reward shaping, right? To bring some formal principles. There's, of course, a wealth of examples outside of my lab on people doing principled RL, including many people here at MIT. So that's the story. Of course, with this story comes a caveat. I started the talk talking about safety being a blocker, and I haven't addressed this at all yet, right? So this is the robot now running outside, doing pretty well, and then, of course, we get a collision, right? Thankfully, it was the stick holding the camera. It wasn't a person, but this does not have barrier functions on it. It does not have collision avoidance, right? And this is what I mean by safety as a blocker, right? When you hit scenarios you didn't expect, you're going to have really bad things happen. And the problem is if this happens in this scenario outside, it's kind of okay. If this happens in your house and your dog's around, or you don't want these kind of behaviors. These robots are actually really scary. And it's also painful. I don't know if you can see my face up there, but I'm kind of cringing. I thought we killed the robot there. I really did. So again, I go back to this question, how do we guarantee safety for these systems, right? So I want to step back for a second now and do a little history, because I think history is important. I think especially in this day and age when there's so much stuff on the archive every day, we forget sometimes that no one lives in isolation, no idea comes from nothing. There's a great quote from Asimov there on exactly this topic. And so people have studied safety for a long time. And it goes back to actually earlier than 1942, but Nagumu's theorem in 1942 is really the de facto standard on safety. And what it says is that if you frame safety as forward set invariance, which is what I'm going to do throughout this talk, we can talk about that. There's lots of other interesting notions of safety, safety on latent variables, semantic safety. There's a whole bunch of things you can think about. But in this case, starting simple, we want to make sure we don't go to bad states, and we want to stay in good states. And in that case, it turns out that back in 1942, Nagumu figured out necessary and sufficient conditions for forward set invariance. And it's a very simple condition. If you have a function h that defines your safe set, it's positive on your safe set and negative outside, then the condition is simply that h dot must be greater than or equal to 0 on the boundary of your safe set, right? Which makes total sense, meaning h dot, the derivative along flows of your system, right? Which says if you're on the boundary and if h needs to be positive to stay in the set, your rate of change better be positive or at worst 0, or it will go negative and you will leave your set, right? So it's very intuitive. Of course, proving it requires a little bit more, but it's very intuitive. People have used this conditions many, many times in the last sort of, 80 years, right? And it's actually been rediscovered on many occasions, including, I won't say rediscovered recently, but used recently in things like barrier certificates, et cetera, right? So this was the state of the art when I approached safety in 2014. Of course, there's something fundamentally missing about this picture. If you want to do controller synthesis, what do you do with a condition that's only true on the boundary of your set? Right? Well, yeah, so the answer is, if I have this condition on the boundary, I'm going to wait until I hit the boundary, then I'm going to see if that condition is satisfied or not, and if not, I'm going to switch to another controller, right? But the question is, when do you switch? And when you switch, is it continuous? Is it smooth? Do you maybe add some buffers in here so that you start switching a little early? Then how early do you switch? How does that matter, right? You can see how you get to a rabbit hole very quickly. So I wanted to ask the simple question, well, we shouldn't do that. We should just have a condition that's true at every point in the set. Then we don't have to worry about waiting to get to the boundary, right? So how do we find that condition? And it turns out that the condition is so again, what control action you take? The condition is actually very intuitive. So the generalization is quite simple. We take Nagumo's condition and we just replace 0 with minus alpha, class K function, but think about it as a constant if you want, of H, right? Then of course, on the boundary, you recover Nagumo's theorem. Right? When H is 0, this says H dot has to be greater than or equal to 0. But inside the set, what does it say? It says that H dot, when you're inside the set, H can be positive, so this whole thing becomes negative, so H dot can decrease. So you can decrease H dot away, and as you get closer, you have to sort of slow down. Now the question is, does that give you the right behavior? Meaning, do you slow down enough? Do you slow down too much? Right? It turns out that you slow down just the right amount, meaning that this is necessary and sufficient for forward set invariance, as laid out by these papers with me and Paulo Taboada, Jesse Grizzle, etc. So this is what is now called modern day control barrier functions, right? And they're surprisingly only about a decade old now. So what do we do with this? So once we have these conditions, we can use them for controller synthesis. But I want to note one thing, going back to Lyapunov, it turns out that barrier functions actually generalize Lyapunov. If you take your set and you contract it to a point, you end up with a Lyapunov function. But in general, barrier functions cover a bigger class of behaviors because they don't have to actually be positive definite themselves. They only sort of have to be positive definite with respect to the set outside the set. So that opens up additional behaviors, meaning inside the set you can move around freely. So again, once we have these CBFs, what do we do with them? And then the answer, I think the second sort of big thing that happened in the last decade was this idea of a safety filter. And this idea came about because actually, we were given these challenge problems where we were told actively we could not modify the nominal controller on the system, which as a control theorist is like the hardest thing in the world to hear. So we were sitting at a table with Ford and Toyota, and we were presenting a bunch of CLF work. And we're like, we'd love to get these CLFs, because I love CLFs, on a car. And they looked at me and they said, that will never happen, right? Why? Well, because we know what works on the car right now and we don't want to change something that works, right? If it ain't broke, don't fix it, as they say. But they said, if you can come up with a control method that lives outside of our current infrastructure, we'd be interested. And that's exactly what these safety filters do. They take any nominal controller, find the minimal modification, subject to the safety constraint. So of course, this gives you kind of a switched controller in essence. It's Lipschitz continuous and smooth in some scenarios that says that if your controller is safe, you let it pass through, and if it's not safe, you need to minimally modify it, project it to the safe set, right? And this is an example of that in action. So on the left, you have the nominal controller, which is actually a really well-tuned segue controller. And then of course, my student in this video is just joysticking it, trying to mess it up, and he can both make it go outside of that yellow region and knock the whole thing over, right? Of course. Now on the right, you pass that exact same signal through a safety filter, and no matter what he does, he can't knock it over or leave the set. Of course, we've deployed this in lots of scenarios. We've done obstacle avoidance. So in this case, you have a human pilot who's trying to crash the drone into walls, and they can't do it. I should also note this generalizes potential fields, meaning you actually get some improved behavior over potential fields. We've done it for multi-robot systems. This was with Magnus Egerstadt. This was actually some of the first experiments with CBFs ever. I was at Georgia Tech at the time, and we put it on multi-robot systems for collision avoidance. So in this case, the grad student, again, is flying this drone and trying to crash it through this swarm of robots, and you get this kind of virtual force field type behavior from the CBFs. So that's fun. And then we also put it on really compute intensive scenarios. So in this case, we have a high-speed racing drone. And we're doing CBFs only on a very small bit of compute on this with onboard sensing. So everything is self-contained. And we're doing geofences. So in this case, you have these regions in space you can't leave. And the student in this case is flying this thing as quick as it can towards these geofences, and the CBF prevents them from leaving the area, right? this same math, and the reason I'm showing all these videos is once you have the math, everything just kind of follows, right? It's like a cascade effect. It's a waterfall effect. Because this same exact method we used on this, we put on an actual jet aircraft. So this is an F-16. This is the Vista F-16. And here we're doing geofencing. So there's a region in space you don't want to go. And at this moment in time right here, CBFs are actually flying the plane. So we're doing safety filtering of the pilot commands to guarantee that we don't leave the region. And we're satisfying altitude floors and ceilings simultaneously. And we're satisfying G-limit constraints, among other things. So making sure we don't have too much force on the pilot. So we can do all that together with a single, actually in this case, a single CBF that filters the pilot inputs. So there's no doubt that these things apply really generally. This led us to a lot of questions, though. For example, one question that we started getting asked a lot was, what about uncertainty? Right? What do you do? Well, we have a whole set of results on input to state stability and input to state safety with respect to CBFs, meaning if you have some bounded uncertainty, you can actually still guarantee safety. But we realized very quickly that bounded uncertainty is fantastic, but we can actually extend this to unbounded disturbances if they're stochastic, using stochastic CBFs. So in this case, we switched to discrete time dynamical systems for which there's a discrete time CBF condition. And we have a theorem that says that if you satisfy this condition in expectation, you're guaranteed to be safe in probability, meaning you can know that you have some probability of staying within your safe set for a finite number of steps. And we can get an upper bound to that, and we can use that to explicitly calculate the safety filter in a stochastic setting. We can collect data, we can sort of learn the distribution, and then from that, get conditions we can actually implement in the safety filter. And so we do this in particular in the context of a drone with an unknown hanging mass. And if you've ever flown a drone and put a hanging mass, you know it's a very hard problem to keep that drone flying. And we did it in the context of geofencing again. So in this case, the student's trying to slam the drone into the ground, and the stochastic safety filter is making sure that that doesn't happen based on the data we collected. And in this case in particular, we updated the reduced order model to account for that learned element. So we can extend it to these uncertainty situations. This is one where we then take that idea and fold it into perception in the loop. So now we're doing onboard perception. So you can see the viewpoint of the drone. And there's balls coming at it, and it has to avoid it. Again, same framework as I implemented before, or I discussed before, but now we're doing this with perception in the loop. And here's another example with perception in the loop, but now we do it to a quadruped. So the lesson here, again, is we first had CBFs, and now we have CBFs with stochastic uncertainty. For example, due to model uncertainty, perception uncertainty, and we can fold all that together in a stochastic framework. So in doing this, we realized a couple things. First, we realized if we just do a safety filter, like I talked about before, it's not as expressive as you might hope. Because remember, safety filters are sort of point-wise optimal, but they're not globally optimal, right? So if you do MPC without a safety filter, you find kind of the inverse. It's expressive. So in this case, the quadruped tries to avoid the ball, but because you're doing just a state constraint, you don't have enough predictive power at that state constraint level. So doing a bunch of experiments in this space, we discovered that MPC plus CBFs is a really powerful paradigm. So everything I presented previously was if you have this one layer control architecture, and now we're going to bring multiple layers together. Okay? So let's see how that kind of works. So by the way, this is a video I just took in my lab the other day. I went down to the lab and the robot was on. This was not pre-planned. We're not trying to do anything fancy here. And I think sometimes just showing the raw experiments really give you a sense of what these algorithms actually look like. So it's by putting all these pieces together, doing MPC plus CBFs, we're starting to get into a very strange uncanny valley now, right? It starts to now when we do lab tours, people actually start to feel sorry for the robot. They think it's getting its feelings hurt and they want to pet it. I'm not kidding you, which is weird. Because previously, they would always be scared of the robot, right? And if you can make people feel sorry for a robot, you're actually, I think, doing your job well. because they're no longer scary, right? So we're starting to see this real improvement. And this actually harks back to work that we did a long time ago. So we've been doing this for many years, where we saw that when we layer these things together, we get better behavior. We get improved performance. So this goes to the second thread that I've sort of been on in the last 5 years in my lab, which is this notion of layered control architectures. So Giulia and me both have done many workshops now on this, talking about how this is a really important secret sauce to making robots work, and it really is. I want to show an example of this. There's no barrier functions here. This is an NPC together with a really good controller. And to me, this is one of my students, Noel, did this. This is just really good control. I mean, he's doing a geometric NPC layer on top of it, but this is my favorite video, one of my favorite videos of all time from the lab. This is a custom hopping robot that he makes hop literally across this plank. That is precise control to hop along a plank that's this big, right? And again, what enabled this precise control? Layered control architectures, right? So understanding, so I started with CBFs and then we started doing this and realizing that there's something really special here. Because once you have these layered architectures, they're actually really robust. You can take the robot outside, can hop in lots of scenarios. This is the cannon you guys stole. I put this video in because, does anybody know the story? MIT stole that cannon from Caltech. They dressed up as security guards, and then they came on Caltech campus, stole the cannon, and they reassembled it on top of one of the buildings here. Yeah? Okay, so that was the cannon. We got it back, though. I don't know how, but we got it back, so it's still there. All right, and so we can also start to do some interesting things like add safety layers back in. But now we can do safety, not at this low-level control, but actually at a higher level using simple reduced order models, right? So what I mean is we can start with really good controllers, and in this case we're doing a safety layer on top of them because this is a complicated controller that has multiple agent interaction with a fixed thing, so it's a really hard control problem. But we can just add the safety layer on top of it and get the whole thing to be safe kind of out of the box. So what's happening here? Well, I'm going to give you guys the secret sauce to implementing CBFs on hardware if you're interested. And it's exactly this, layered control. So I showed you nonlinear dynamics earlier, and that's a lot of fun. But let's step back for a second and just say, let's suppose we have some reduced order model, and then we want to put a safety filter on that reduced order model, and that's going to feed into some full order dynamics. This full order dynamic model is being run by some controller that tracks that reference. We don't care what this is. This can be a policy, an RL policy. This can be a VLA. I don't really care. All I know is that whatever it is, I need to take velocity as a reference. That's it. And then I'm going to have my own controller sitting up there, my own internal reduced order model that I'm going to use for the safety filter. So think about it like this. Every element of an autonomy stack has its own model. If it's RL, that model was a simulator. If it's a safety filter, you're probably going to have some simple sort of maybe kinematic model. And in this scenario, you can formally guarantee safety without knowing what's happening down here. What I mean, and this is the theorem, is that if you have sufficiently good tracking, so that's what's up here, if you have, in this case, exponential tracking of this reduced order, of this full order model, oops, too many slides. If you have sufficiently fast exponential tracking, then you're guaranteed that your system is safe, meaning the full order dynamics of your system is safe, buffered a little bit by this tracking error, even if all you have is a reduced order model generating reference signals. Okay? Makes sense? And how does this work? I mean, this kind of blows my mind the first time we figured this out, which was about 2022. Take your reduced order model to be the single integrator, simplest system imaginable, right? Take your barrier function to be don't hit obstacles in the environment. Then your CBF becomes this, and this is your safety filter, which is literally like I'm writing it down. It's like 2 lines of code. Put that safety filter on a quadruped and just modulate the joystick command. You get collision avoidance, right? Take that exact same controller, put it on a drone as the reference command, you get collision avoidance. Right? So understanding these layers mean you can really rapidly develop things. And of course, you can change the reduced order model. You can put like a unicycle model on the quadruped and do the same sort of, you're going to get a more complicated safety filter, but the same thing applies. So, of course, there's trade-offs here. I mean, if you use a simple reduced order model, you're going to get fairly conservative behavior. It will guarantee safety, but it will be kind of conservative. The better reduced order model, the less conservative the behavior will be, right? But this works in a lot of scenarios. So we did this on a manipulator. So in this case, Our barrier function is actually a signed distance function with every point in the environment for which we have a simple just single integrator reduced order model, which we pass as a reference velocity to low-level control on the manipulator. And the one caveat here is because the signed distance function is not smooth, we had to find a smooth approximation, which gave you a small gap that you had to account for in the CBF condition as a delta. I say this because it turns out that my final sort of theory piece on this is you have to pay attention to the deltas here. These matter a lot. What I mean is, if you try to do a reduced order model without a delta on really complicated systems, you actually can get safety violations. And the reason why you can get safety violations, even though it doesn't look minor, is because exactly this, the tracking controller we prove that you get stability of a slightly enlarged safe set when you have a tracking controller. If you don't account for that enlarged safe set, you're going to get slight violations. So if you want to make things better, you got to buffer with a delta. So this actually leads to input to state safety and a whole bunch of beautiful math that was in a bunch of papers, if you're interested, on how you can robustify the implementation of reduced order models in this way by picking better deltas. And in fact, there's a theorem that says this works, so I want to be sort of explicit. What it fundamentally means is, before, without a delta, if you have this tracking, okay, you need to have exponential tracking all the way down to 0 to guarantee safety, which is never in practice true. What the delta gives you is the ability to replace this condition with bounded tracking, which any real system, you'll have bounded tracking, right? So then you can recover this theorem that the full order dynamics is safe, even if you only have these reduced order dynamics, as long as you add a delta accordingly, in essence. And that delta led to a lot of interesting things like collision avoidance, locomotion, this hopping robot doing collision avoidance. So we've been able to really study this in a lot of different contexts, what the role of delta is. Okay? So that's the story. So that's the layered architecture story. So what do we do with all of this stuff I presented to you so far, right? How do we handle all of these pieces? So let me sort of recalibrate for 1 second, because I know I can it's always hard for me to give talks because I love all the work we did in the lab so much. I want to tell you about all of it, and I have to kind of like step back and only tell you pieces. And so I already told you a bunch of pieces, but why does this matter to the original problem I posed? So let's go back to humanoid robots now. Now the videos I showed at the beginning of the talk, they had a bunch of subtext in them that that at the time you probably didn't catch, or maybe you did. First, what model were we using for the safety filter? Right? Was I doing a full order dynamic model with all the joints, like nonlinear model for the safety filter? No. What model was I using? The answer is actually on the slide. Single integrator. There it is. Single integrator safety filter on the humanoid robot, and this is the behavior you get. It looks super dynamic, right? To imagine a single integrator gives that kind of behavior. Why? Because you actually have really good controllers below the surface. In this case, this is actually Unitree's RL walking controller, which is actually pretty good, of course, as you know. So the better the controller gets down below, the better our safety filters get, even with reduced order models. And now we, of course, know from the second part of the talk that we actually get a formal guarantee of safety on this full order system, even though we're only using a single integrator reduced order model. So we have a theorem that says this thing will actually be safe, right? There's one other piece I didn't talk about, though, yet, that we have to fold into the picture. Anybody have any idea what that is? What's the missing piece? I talked about the models. I talked about how I'm implementing, so you should get a pretty good sense. It's actually the clues on there. No, the learning's sitting here. I'll talk again about learning. And we can do this with CLFRL2. That's, we're sort of platform agnostic. It's sitting on the board, right? It's sitting on the TV right there. Perception. How do we handle the perception component? So that's the last bit that's made a huge difference. In fact, I'm going to make a statement here that's pretty strong. Perception is in many ways, and how you handle perception in many ways, much more important than the model you use for a safety filter. Single integrator model with really good perception handling makes all the difference. What do I mean by this? What's happening here? So this is actually a recent result that was at RSS this year, but I really like it a lot. It's really beautiful. What we can do is take perception data, whether it's LiDAR or camera, it doesn't matter. We can solve, and this was a result of my students and postdocs, where they came up with this idea of solving Poisson's equation, a PDE, and they can do this in real time at faster than a kilohertz, super fast. to build a single functional representation of the environment that's smooth for any number of obstacles. So much better than sine distance function. And the end result, this is with a single obstacle, you can do it with many. This is your Poisson safety function, as we call it. Of course, positive means you're safe, and as the ball rolls through the scene, you get this negative bit, which is unsafe. And then, of course, we'll also have a safety constraint that we don't leave this set here, so we get 0 along the boundary. And this determines H. And that's what I'm really pointing out, is that if you look at a safety filter, what matters? You have your model, and you have your barrier function, H, and you have the gradients of that H. All of those pieces are as important as one another, right? And this is addressing the H. The model itself in this case is very simple. So this is a method, this is just the same thing, but now if you watch the screen back here, I think you'll appreciate much more what's happening, right? It's real-time synthesizing the barrier function, solving Poisson's equation. And again, this is just Unity's off-the-shelf RO, and my student just interacting with it, which is, I like this video. By the way, this also worked in one day. And I only say that because, to me, a sign of the math being right is you put it on hardware and it kind of works out of the box. If you have to force it uphill, you're probably not, you're missing something. Here's another example where we actually added a couple pieces. First, we had a geometric representation of the robot in the Poisson's equation. And second, we were actually doing this predictive safety filter, which is a CBF condition in an MPC problem. And that gives us this predictive behavior. So as the ball comes, we don't just go out of the way, but we actually turn and rotate to avoid the collision. You can actually see on the screen the trajectory from the predictive safety filter together with the geometric representation, all being done in this Poisson safety function. Right? So that's the perception part. Again, going back to this, we can close the loop on some of the other stuff we did as well, though, right? So I talked about stochastic CBFs earlier. That was a lead into this. Again, I told you we were doing single integrator reduced order models, and they work really well. True, but we can also make them better. How do we make them better? We can collect some data from the deployment of the single integrator CBF on the hardware. We take this data, and we can learn the distribution, and then get a stochastic guarantee on safety, and we can learn a better reduced order model that we can then use for the safety filter. And this better reduced order model, this D here that we're learning, includes in it, I keep hitting too many buttons, includes in it, sort of contains the RL policy that was under the surface here, right? And so this is what happens when you do this. Our learned reduced order model has much better tracking than the original one. Better tracking means smaller safe set expansion, which means tighter performance. Right? So that's where all these pieces start to come together again. I'm trying to really demonstrate the interplay. And once we do that, we can get really cool deployments. So this is now this safety filter, but using this learned reduced order model together with stochastic CBFs outdoors. So we're doing obviously onboard compute, onboard perception. This is actually the perception in this case. So these are the obstacles the robot's sensing in real time. That's my student Gary, who it's avoiding. And this one's kind of cool. Again, anytime you take a robot outside in the real world, the humanoid, first, it's super cool. And second, you get really big crowds. I don't know if you've noticed this. This was just us taking this out. We didn't tell people this was going to happen. And pretty soon we had like 50 people watching the robot and wanting to interact with it. There is a very visceral connection with humanoid robots. So anyways, this is cool, though, because now we have really closed the loop. So there's one element, though, we haven't like fully closed, though, between all the things I talked about so far. And it was said earlier. Now you can say it again. What do we need to bring it back to? Learning, okay? So is there a role for learning? So everything I did, yeah, we learned the reduced order model, but that's really like learning for control, which is very important, learning the reduced order model. But can we take these ideas and actually bring it to the learning community? And so this is a recent result that is sort of in that light, where we can actually do CBFs in training to inherently learn safety filters using all of the tricks that we've assembled so far, if you'd like, right? So what happens here? We have some RL policy, and we want to roll out this RL policy together with a safety constraint. So in this case, the safety constraint I'm showing here is the stairs. We don't want the feet to hit the stairs ever, right? Because we want to walk up and down stairs. We can also do it for collision avoidance and other things, whatever you want, right? So how do you do this? Well, you're going to roll out your policy, but as you roll out, you're going to safety filter. How are you going to safety filter? Well, I showed you earlier the rollouts themselves. So our actual model in this case is the simulator. We don't know the model, right? But for the rollouts, we can use a reduced order model. I showed you how good an integrator works, right? So let's use a single integrator reduced order model, but now discretized. And then for this, we would have a discrete time CBF condition, which I talked about earlier. I keep hitting the wrong buttons. There we go. A discrete time CBF condition. Well, it turns out you're able to prove that you can enforce the continuous time CBF condition, and that implies that the discrete time condition is satisfied, which means your rollouts will be safe. So we can go from continuous to discrete, and from the rollouts and reduced order model to actual safety on the full order dynamics, which in this case is just the simulator. Why does that matter? Because once we have the continuous time condition, this is F fine in your input, hence you get an explicit solution. You have an explicit solution, you can do what? Why do we need an explicit solution in this case? Anybody? We can GPU parallelize, right? We can't yet GPUs parallelize QP solves, not effectively. There's people working on it. But explicit solutions means it's like 2 lines of code you add to your rollup procedure as you're doing the RL, meaning there's no real computational overhead, which means now you can chain at the rollups, and then the final step is you bring all that back. You take this, if safety is violated, you take the correction term, you fold it back in, and you take your nominal reward and modulate by this CBF. So the reward has some knowledge that you're modulating this output. And you put all those pieces together, and this is actually now, you deploy that on hardware straight up. And you can do stairs. In fact, let me show you the outdoor montage. So this is now CBF-RL with CBFs in training. There's actually no online safety filter here. We sort of learned the behavior. Now, in practice, I would do an online filter as well, just to be very clear. We're just showing that this works without one. And we're able to handle pretty dramatic stairs. I mean, we have a ways to go to make this super smooth and fluid, to be clear. This is a very recent result, but I'm kind of showing where things can go when you start to inject now control into learning, right? Meaning what we know about control into the learning-based procedures, right? One more time because it's pretty. I love watching robots, right? So that's kind of bringing everything really back full circle, right? Make sense? See all those pieces? So in the end, you have this repertoire of things that we've developed. So in particular, I'm going to go back to this statement of why learning needs control and control theory. And I will say the converse is also true. It's not in the slide, but I want to really clearly, emphatically say that control also needs learning. We need each other, right? We need each other, and we need to find these common intersection points, okay? So on one level, why does learning need control? Because control can help address the bottlenecks that learning inherently has. Learning does great at performance. It is not great at robust, certifiable, safety-critical behaviors, right? Control theory has a century of making sure that airplanes fly with 10 to the minus 9 safety, right? We need to take those principles, things like safety filters. I mean, here we have a certification that our system is safe, that we can use to verify and certify the system in many contexts, and we put this in independent of your RL algorithm to guarantee safe behaviors on the system, right? So that's what it can do on that end, and then coming back again, control-guided learning can help to unlock performance. So I actually think going beyond just safety filtering, control can genuinely help learning be better. Right? And these are 2 examples from my lab. I mean, again, I say in all humbleness, I mean, these are a couple of grad students, incredible grad students that did this, right? But I don't have 100 people in a company like pushing forward the latest like reward function shaping. And that's the beauty of math, is this a couple grad students, really smart grad students. I don't want to downplay this enough. These guys are brilliant. But we can get really good running. I'll put this up against any of the state-of-the-art running I'm seeing right now. Right? And it's all based on just clean CLFs and 2 weeks of deployment. Of course, the stair climbing too, which is very cool. So we can use these control-based principles to inform reinforcement learning and other methods. This talk, so my final piece is this talk really focused on RL specifically. There's, of course, a lot of other ways you can do learning, VLAs, etc., large language models. And I think in all those cases, again, similar messages could be made. I'm just not an expert in those domains, and I don't want to talk outside my box. But in this case, I hope at least I've made a reasonably compelling case as to how we can work together in this front. And so why do we want to do this? So I'm just going to close with 2 fun videos. First, the CLF-RL was actually invented out of necessity. right? The great quote, necessity is the mother of invention, right? So we had to do this demo, and we had to get the robot to walk really well in a lot of different scenarios with different loads on its back. And I couldn't imagine the reward, like shaping and tuning we would have to do to make that all work in a month. So I worked with my students. I'm like, we have to find a principal way to generate different walking behaviors. In particular, we rolled out CLFRL for the first time in this scenario. This was literally 2 weeks after we invented the idea. And why, again, this humanoid robot, this is the G1, is carrying this drone. It's more than just a drone. It's actually called M4. So we had to walk with it, and that's CLFRL. Then we had to do this behavior of bending over. Why? Because you don't want to carry a drone unless it's going to go somewhere. So then the drone takes off, flies away. So what you're trying to do here is leverage the locomotion modalities of each platform to its greatest benefit. So then it can transition into a driving robot and back to a flying robot, right? And it can take off. So it's able to explore a lot of spaces that might be hard for a humanoid. Right? It can get a lot of places, like here it's flying over the turtle pond at Caltech, and while it's doing that, the humanoid can walk around sort of the long way. So outdoors, the drone and the M4 in particular can really move around quickly. Of course, inside, you probably don't want that drone flying around the hallway, and the wheeled robot certainly can't go upstairs, right? So that's where the humanoid can really flourish. In fact, the stair climbing, again, was invented out of necessity. This was the first time we ever implemented that stair climbing idea, and we did it pretty successfully. So this is actually what led to a lot of these inventions. It started at math, and a month later we were doing these things, and this is where you'd really like to take humanoids, really outdoors doing real world things, right? And of course, ultimately, my interest is humanoids around people. These are just students around Caltech that stopped to watch the humanoid, and we're running a safety filter. Using the LIDAR from the one I showed you earlier called SHIELD. And my student here is just kind of, this is an autonomy. He's driving the robot around, but we know and feel confident that it won't run into the people because it's got a safety filter on it, right? So again, this is the final bit, which is we'd like to deploy these robots in places around people, and to that we need to have real confidence that it will really work in real world scenarios, right? And underlying all of that, and I'll go back to my origins, is math. Right? I mean, math is the great unifier. Math is what makes it all work. And one simple equation can go a really long way. So with that, thank you very much.